This is my last lecture. I'll probably make a concluding video after this also, but this is going to be the last one that contains mathy content. We are at the end of chapter 5, which is titled Further Integration Formulas in our book. It's not the end of learning integration. This is the end of the introduction to integration in our textbook, and there are many important things that come after this that will continue on in Calc 2, continue on in Calc 3, and continue on as you would take differential equations, learn partial differential equations, learn numerical techniques. It goes on and on and on. You never reach the end. This is not done. There are people who still work on techniques for integration. So I want you to know a few more integral formulas, and really more than that, I want you to know techniques for integration. Particularly, we're going to play with stuff in the back of the book in the tables of integrals, and I want you to learn how to use those. And there's some really cool stuff that would come in Calc 2 in integration by parts, which undoes the product rule that I'm not equipped to do with you right now. And that comes in Calc 2. I'll point your attention to 2 Lightboard videos that I have on this topic. And we'll just dive right in. Basically, we're going to do this page, which has some integral formulas on it. I'll do 3 examples and give you some advice, and we'll call it good. And then we'll just have to take this class to conclusion. We are so super close, and I'm really proud of you for being here. This section in the book has a few more integration formulas, and this stuff is on page 347 of our textbook, where they do a little bit of derivation of some new formulas. They do a derivation for a definition, maybe, or at least a relationship of the natural log function. There are many ways to write out the natural log function. So natural log can be expressed as the integral from 1 to x. It's the area under 1 over x, which is really cool. I think this relationship is really freaking surprising, to me at least, and I think it's really cool. There's one right here, which is an arcsine definition right here, and which is part of an area underneath this weird 1 over a circle kind of deal. So that's pretty wild. In Calc 2, particularly when you do trig substitutions, wherever that comes in that class at this university, that's where you would learn how to derive something like this and do much more complicated things with it. And you can't, this is because it's inside of a circle, and so if you go past -1 or past +1, then you'd be out of bounds and you start getting complex numbers. This one right here is the integral of the generic exponential function with base other than e, and you pick up this 1 over natural log, because when you differentiate, you pick up a multiplicative factor of 1 of natural log of b. Fine, whatever. Okay, so these 3 formulas are fine and dandy. And then the book goes on to give this inverse trigonometric functions blob that I have on the screen right here. We've got some derivative formulas right here. Those were given to us back in one of the last sections of chapter 3. I didn't cover them in depth. I don't feel like they're particularly super duper important. Maybe one of my colleagues would chew me out for not doing that, whatever. And correspondingly, we have the integral formulas, which basically you just throw an integral on both sides right here, put a dx, stuff cancels, and you end up getting arcsine plus some constant c is the integral of these things right here. I don't explain where they come from. I do have one video on YouTube related to the end of chapter 3, where I derive the derivatives of the arc trigonometric functions, the inverse trigonometric functions. Fine, you can go watch those if you want. I'm guessing 0 people will. I don't blame you. Okay, so this page is fine and dandy. Congratulations, page 347 has these formulas on it. I think that's all fine and dandy, but why stop there? there's this whole section in the back of the book that we have never referred to that I want to use for this section because it enables you to do a bunch more things than I can possibly cover in one lecture. And so what I'd really like to do is I'd like to refer to the table in the back of the book and train you a bit on how to use it. I wish we could all like bust out our textbooks together in class and like try some of this stuff together. But unfortunately, we're separated by time and space. Fuck COVID-19. I want you to go to the back of the book. This content is really awesome, and it's so great they didn't even number the pages, so I can't tell you what page number to go to, WTF. But I want you to find this section on integration in the very back of the book. It says integration in magenta. I believe I'm using the exact same color as them. If you go to the super duper back, there's like the big thick piece of paper. Can you hear it? The big thick piece of paper, and then one thin piece of paper. You flip it, and now you've got this big spread of integration formulas. I thought about like taking pictures of them and putting them in this presentation, but you know what? You have a book, and table of integrals are not hard to come by. So go ahead and pause the video and take a look at this, and you'll see some familiar stuff under the basic forms. And then we start getting into the slightly more complicated stuff. And there's no explanation of how these were derived. There's only forms. And so I want to do a little bit of how to use them with you. And this all has to do with substitution as well. So go ahead and pause it and take a look at this sheet. And I particularly want you to look at 58 through 66. And maybe like 84 and 85, because those are the ones I think I plan on working with. All right, so give those a whirl. And then unpause it, and then we'll go ahead and do this this very first integral here. And we're going to use the table to do it. Okay? All right, welcome back. Thanks for unpausing me. So I'd like to work on this integral right here. And what I'm going to do is I'm going to look, I swear, I'm going to look for this in the back. And just cruising for this, I'm looking for u over u to the fourth plus 1. I don't see any u to the fourth. I see a whole lot of u squareds. U would just be x if we found it just as it is. So I don't see it as is. So what we're going to do is we're going to try doing a substitution. Let's try doing a substitution. So we failed to find. So let's try a substitution. Okay. So you might be like, okay, cool. Well, let's try a thing. Let's try letting u be the stuff in the bottom there, and maybe this can turn into a log, right? So let's try u equals x to the fourth plus 1, when then du is equal to 4x cubed dx. But unfortunately, I don't have an x cubed right here. I just have x to the 1. So I fail. I failed to be able to substitute. Okay, so that's no problem. I'm not willing to give up. I think we should try something else. And that's, I see that there's a 1 right here. Right? I see that there's a 1 right there. And if I try letting x squared be u, then I'll pick up when I take the derivative of an x to the 1. So let's let u equals x squared. So then du is equal to 2x dx. All right? So let's introduce a 2, as we've been doing. So we have the integral of 2x dx over x squared plus 1 is how that's written. That's equal to a half of the integral of du over u squared plus 1. And now we're going to go look, right? Because there's lots of stuff with u squareds. So go ahead and pause the video and cruise. I'm going to cruise it too. I'm not going to pause because it's impossible for me to do. I'm cruising. I'm looking essentially for like du over u squared plus 1. du over u squared plus 1. du over u squared plus 1. Let's see here. I see u squared plus 1. Where is this one at? Ooh, I see it. I see one. It's got an A. It's got a placeholder, right? So let's let that be A, and A equals 1. So that's A squared. Okay, that's number 16. Do you see it? Do you see how that's number 16? All right. So number 16 says the integral of du over a squared plus u squared equals 1 over a times arctangent of u over a plus some constant c. Great. All right. That means that this thing here is equal to a half of, let's see here, so a is 1, so this is going to be 1 over 1 times arctangent of u over 1 plus some constant c. It doesn't matter whether I put the c on the outside or not, it's still an arbitrary constant. So let's simplify this and write it as a half of arctangent of u plus some constant c. And then we'll go ahead and complete the substitution. 1 over 2 arctangent of, we said u was x squared plus some constant c. Not that bad, right? So do you see the pattern? It was like, try some stuff. We're just going to look for the original function. And then we're going to like try a thing. And if it doesn't work, then like, okay, like what did I lose? Like 3 seconds, 10 seconds, 15 seconds, a little bit of frustration? Fine. I've had much worse frustration in my life. Like one time when I microwaved a bowl of 3 packets of instant oatmeal and it was so hot I dropped it immediately and it took me an hour and a half to clean up shattered glass and scalding hot oatmeal off of a floor, right? That was much more frustrating than this failure to substitute. So then we tried something else. And how did I know what to do? Well, I was like, well, I want to get rid of that thing in the top there, right? I see an x to the 1. What do I take the derivative of to get to an x to the 1? X squared, cool. And then I just like work it in like that. How did I know what to do here? Practice. I knew because of practice. And this section in the book, 5.8, has 74 problems in it from beginning to, that are just integrals for you to do. And I really wanted to assign all of them. I want to assign all 74 of them. And I'm going to decline to assign all 74, even though that's the thing that would make you good at it. I want to make you work scales, the complicated scales, for like 2 days straight. Because that's how you get good at this. But I'm not going to do that. And so it's up to you to really take ownership of this content. It's only through repetition that you gain mastery. Let's try another problem. Let's try to do the integral of x root 9 minus 4x squared. Alrighty. This is looking pretty interesting. I like this problem already. So I think one thing that I might do is rewrite this as the integral of 1 over x root 9 minus 4x squared dx, because I know that a lot of you are more down with that. And then, like, okay, so here's the thing that I think probably people are thinking at this point when they look at this function. They're like, ooh, an x, minus 4x squared. So they're going to want to be like, try u equals 9 minus 4x squared. So then du is equal to minus 8x dx. And then I'm going to be like, but no, that totally doesn't work, because the x right here is in the bottom, not the top. I need to have x dx, not 1 over x dx, right? So this substitution fails. Wah, wah. It's my sad face. Wah, wah. Boop, 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 boop. And that's okay. So we got to do something else. I might pause and look at the table for something that looks like u root blah minus u squared. And then we'll moosh it into this form if we can find it. Oh, sorry, 1 over. Boop. All right, so I want you to look for this in this table. I'm looking too. Ooh, this is looking pretty promising. Look at the magenta heading. Look at forms involving square root of a squared minus u squared. All right, because I have a squared minus u squared. If I just make that thing be a squared, then I'm in this form here. All right, so I'm looking for 1 over. I'm looking for I see it. Let's see here. Yeah, I think this one's looking pretty good. Number 72 says that the integral of du over u times the square root of a squared minus u squared equals minus 1 over a times the natural log of the absolute value of a plus the square root of a squared minus u squared over u plus some constant c. I don't care how much you don't like that. I know like 3 of you just now were like, I hate that, and I don't care. The integral doesn't care what you think about it either. We're still going to do it. The point is that you can use a table, and using this table, you have significantly expanded capabilities for computing integrals than you did without the table. And using the table, all of these functions are just the same as all of the other ones. There's no point in me restricting us to those things that I showed you just on the front there. Using this table, we can do all sorts of crazy things. Okay? So now what I want to do is I'm going to try to moosh the integral of 1 over, why does it always consume those if it's still scrolling? I think that's a bug. Square root of 9 minus 4x squared dx to look like the integral of 1 over u times the square root of a squared minus u squared du. And I think this is going to work out. It's possible that things won't, but I think it's going to work out. I don't promise I always know what I'm doing. All right, so let's then take the integral of 1 over x root 9 minus 4x squared dx and start playing with it. What I'm going to do is I'm going to get this 4 out of here, okay? 1 over x square root 4 times 9 quarters minus x squared. I think I better keep going horizontally. There's a reason I left these pages, this whole pages for these problems. This is one of the points in the class that people like to be like, problems are getting really long. And I'm like, yup. There are famous math papers where the proof is like 200 pages long. All right, so let's rewrite this as 1 over x. Let's pull a 2 out front. Let's not write that in the stupid order. Let's call that 2x. Square root of 9 quarters minus x squared dx. I'm going to pull that 2 out front with a 1 over. That is so freaking cool. Now let's rewrite that as half of the integral of 1 over x times the square root of 3 halves squared minus x squared dx. Now, does that fit this? Yes. It does. So by number 72, this is equal to a half of, let's see here, we're going to invoke this crazy thing that I have right here. That is just the worst 2. There we go. All right, so we're going to put that in. This is our friend A. So I need to have minus 1 over 3 halves times the natural log of the absolute value of 3 halves plus the square root of 3 halves squared minus x squared all over x plus some constant c. I think there's some simplification available to us, and we should totally do it. Let's move that minus sign out front. Let's write this as minus half. Let's flip that and write that as 2/3. It's a dot. Natural log of 3 halves plus 9/4 minus x squared over x plus some constant c. And I don't really want to rewrite all of that. That sounds terrible to me. So let's call that minus 1/3 out front there, shall we? That, seriously, like, you just follow the rules and do what the table tells you to do. It's not that bad. So this is one of the sections in the book where students resist me. And they're like, why do I need to bother with this shit? And I'm like, because it's not about these functions, right? It's not about these functions. It's about the technique. It's about the technique. And I think the technique really comes and shines when you learn how to use this table of integrals. How many integrals are in this thing? 111, right? So you can live small in a corner, or you can learn how to use the table of integrals and know how to do 111 different types of integrals simply by looking at pieces of paper. Okay? All right, so let's do one more of these. I think this one's pretty cool. I never do this one. Yeah, okay. Yeah, so let's do this one here. All right, so again, I think the knee-jerk reaction, my impulse, is to let u equals like x to the 4th minus 1. So du equals 4x cubed dx, but I fail because I don't have x cubed in the denominator. Or, sorry, the numerator. Right? So this doesn't work. And there's nothing wrong with that. It's not bad. It just means we've got to try something else. All right, so let's try something else. Let's try let's try that. Can we try that same game again? If I do that, then I think I'm still not any better off, because I think I end up with du equals 2x dx, and I again don't have the x in the numerator. Let's see, how did I plan on doing this one? I think it's okay if I don't have an answer to it. I'm looking in this book again to see if I have any stuff. So I'm looking for forms involving like square root of u squared minus a squared. I'm not quite seeing it right now. Let's see. I'm cruising in this table here because I'm stubborn. And I think you should be stubborn too. So this feels like, to me, so I've got like u minus a kind of action, like square root of u squared minus a squared kind of action. I'm not coming up with an antiderivative formula for something that looks like this. I see various ways to make this thing more complicated, but I don't see many ways to make this thing much more simple. Let's see here. So if u is x squared, then this thing would turn into the integral of, how am I going to get that dx? Okay, so if I have, what if I multiply by like x squared? No, what if I multiply by, I've got an idea. All right, I'm just trying stuff here. What if I go x over x squared root x the fourth minus 1 dx? So do you see what I did there? I multiplied by x over x. Ooh, that's just 1. Because it already couldn't be 0, so x couldn't already be 0, so like this was already acceptable. I don't have to justify that. The function already had a singularity at x equals 0. Ooh, okay. Oh, this is so good. Oh. All right, so now let's do this. So this is the integral of x over x squared times the square root of x squared minus 1 dx. And I've got myself a u, and a du. I've been practicing my substitution method, so I've gotten good at that. Have you? So this is equal to 1/2 of the integral of du over u times the square root of u squared minus 1. All right. Okay, so we made progress, I think. So now we're going to go back to the book, and we're going to look. It's not the same as the last one. Because okay, so you might be like, well, we just did this one. But no, I've got u squared minus 1. And in the previous one, I had something minus u squared. And those are different. So I'm looking. $80 is pretty close, but it's missing a piece. 72 again is close. No, it's gonna be in the section forms involving square root of u squared minus a squared. What if I do that? What if I do that again? What if I do that again? What if I go u and put a square there, and then I let v equals u squared, so then dv equals 2u du, and then I put a half and a 2, that's dv. I've got a v and a v, and I can rewrite this as a quarter of the integral of dv over v square root of v minus 1. Now I'm looking. I think I know what to do for the next step. And that's because I paid attention in the substitution. There was this one weird example that stood out from the rest, and that it was like kind of this like two-step process. So I think I want to let... All right, so now I've got... Okay, so I've got a quarter of dv over v root v minus 1. Let's let w equals v minus 1, so then dw equals dv. And I also know that w plus 1 equals v. All right, so we're going to do this substitution for right here, and we're going to do this substitution for right here. This thing right here is dw, so this is equal to a quarter of the integral of dw over w plus 1 times the square root of w so a quarter of the integral of dw over w to the 3 halves plus w to the 1 half. And unfortunately, that doesn't split. I don't know if I like the previous one more than this one. I think I might bail on this one. I'm not quite ready to give up, but I'm feeling pretty negative about this, because I can't integrate this as is, because I can't integrate just a product of things. I don't know how to integrate this. Was this any better? Was this better before I had it? I don't think so. I really thought that I'd have it once we were at this stage right here. Again, that was, I had a half of the integral of du over u root u squared minus 1. I think I'm saying a lot. It's because I'm thinking. Oh. Yeah. Okay, so, well, why doesn't that one show up in the back of the book? Did they forget to add some to the back here? Okay, so look at page 304. 347, shall we? Look at page 347. Or if you want, oh man, do I just need to flip the page again? Where is arctangent in this table? Where are you, arctangent? You might be getting frustrated with me right now that like I didn't just know how to do this. And I think that you should probably doubt that, because I think that the requirement that everybody who is an instructor for you know how to do everything the first time they do it is unrealistic. One, it supposes that they already know how to do everything, which they don't. We're all human. But also, it means that you never get to see them think on their feet if they already have all the answers thought up, if they have already planned through everything. And I think there's a lot of value in you seeing me work through this process right now. Okay, so there's some stuff that's missing from this table. I now have complaints about this table. I want you, okay, it was in this packet. Let's flip back to 3 pages, okay? Let's flip back 3 pages. Boop, boop, boop. Look at this one. So if I have that abs x there, which I don't in this problem, but I'm so close, then I have this. So if I just restrict, if I take this right here, and I suppose that that u is bigger than 0, then absolute value of u is equal to u. Oh, no. Then this totally works. This totally is it. Oh my God, this is so freaking cool, everybody. You are in for just a so super treat right now. All right, are you ready for pure enjoyment? For magical ice cream? So look at this. Where'd this substitution go? Look at this action right here, right? Look at this. That implies that u is always bigger than or equal to 0. Look, because I have x squared. X squared itself is bigger than or equal to 0 because we're squaring a real number, right? So the absolute value of u is u. Yeah. Okay, so this thing is equal to the half of the integral of du over the absolute value of u times the square root of u squared minus 1. And by that formula, this is formula 4 on page 347. That's a B. By 4 on page 347, this is equal to secant inverse of u plus some constant c, which is equal to secant inverse of x squared plus some constant c. Oh, wow. Okay. So all of this down here, really. So this stuff right here, that was just extra sidetrack. That was extra sidetrack. I think it was valuable sidetrack because you got to see me think on my feet. Because hopefully that introduced you to some like other things that one might do to try to manipulate these. Right? Ultimately, it was like being like, is there another thing that I'm missing? So you might want to add number 4 from page 347 to that table of integrals. Go ahead and get a pen out and deface the book and add this in because it's missing. Why did they leave it out of the table? That's dumb. All right, so we have our answer. Secant inverse of x squared plus c. All right, one more. I couldn't stop myself. I just love these problems so much. I love them. All right, so go ahead and pause the video and you try something. Probably you use substitution, and then we're going to use the table. All right, so you paused it, and then you unpaused it, and you tried something. So it might be tempting. And oh, I am tempted. I am so tempted to let u equals sine squared of x. Well, then du would be equal to cosine x sine x with a 2 dx. And then I can rewrite this as a half of 2 times cosine x sine x root 225 sine squared x dx. And this part right here is our friend du. I've got this right here is u. Oh. And that's like 3-day-old leftovers. Nobody wants those. That's such a bummer. I'm so sad. I'm not really sad. It's a thing that happens. I try things. They don't work. That's okay. That must not be a great choice for you. Sometimes multiple u's work. Sometimes there's like a u that's really going to lead you the way. So let's try copying again. So let's start over. The integral of cosine of x sine squared x root 225 plus sine squared x dx. Pause the video and try something else. Unpause. Okay, so let's try. I think that I should let that right there be equal to, oh, no, we already tried that. What if I let u equal sine x without the square? So that's going to be u squared. I think I should do that in a different color. Boop. So that right there is going to be u squared. That right there is going to be u squared. Then all I need is for that cosine x to be taken up, and it's going to be, oh, I love it when this works out. du, purple, du is cosine x dx. Integral u squared square root 225 plus u squared du. Integral u squared square root 15 squared plus u squared du. Look in the table. Can you find anything? Essentially, we've got the square root of a squared plus u squared. Do you see something? No, it's not in 1 through 16. It's not one of the basic forms. It's not exponential or logarithmic. When it's not a hyperbolic. It's not trigonometric. It's not inverse trigonometric. It's not a form involving square root of a squared minus u squared. It's not a form involving square root of u squared minus a squared. Ooh, though. It's a form involving the square root of a squared plus u squared. Ooh. Look at number 85. Number 85 says that the integral of u squared times the square root of a squared plus u squared du is equal to, for the sticklers out there, I'll adjust that. Ooh, oh, this is great. Oh my God, this is just ludicrous. U over 8 times a squared plus 2u squared times the square root of a squared plus u squared minus 8 to the 4th over 8 times the natural log of u plus the square root of a squared plus u squared plus some constant c. Oh my God, this is amazing. Like, how could you not agree with me that this is truly amazing to go from here to here, right? Look, it's in a book. All I have to do is know how to use the book. And I get to do this, 111 of them. Oh, I love mathematics. Equals. U over 8. Okay, so what's U again? U is sine. Sine x over 8 times 15 squared. How about I just write 225, okay? Plus 2 times sine squared of x times the square root of 225 plus sine squared of x minus 225 squared. Ooh, I'm going to reach for the calculator on this one because that's 15 to the 4th. Fine, I'll just do it as 15 to the 4th. It's fewer keystrokes. 15 to the 4, enter. 50625 over 8. Those numbers are relatively prime, so there's no simplification there. Times the natural log of sine of x plus the square root of 225 plus sine squared of x plus some constant c. Wow. Oh, if that doesn't satisfy you in some weird way, oh, I don't know what will. That is just amazing. Oh, wow, I just got like chills. It wasn't quite ASMR, but it was like, wow. All right, you're probably sick of me being amazed at this ludicrous line of mathematics that we just wrote down. But like, stare at it for a second longer and be like, yes, that's amazing. Okay, let's turn the page. I have general advice for you. I don't think I've put an XKCD comic in any of my lectures yet. It was time. Differentiation is pretty straightforward. Randall Monroe agrees, right? It's basically like the chain rule, the product, or the power rule, the product rule, the quotient rule. Like, you know how to do those. Like, those are pretty straightforward. And like, are you done with it? No. Then like, do those things again. And otherwise, yes. And you're finally done. Great. Integration, on the other hand, yeah, this is pretty accurate here. So let's like try integration by parts. Again, I'll remind you that integration by parts, that's coming in Calc 2. Why do I keep writing letters out of order? What is wrong with me? So that's in Calc 2. We're doing substitution in section 5.7. Somewhere in here should be like a table of integrals. Are you done? No. There's this partial fractions thing right here. That's in Calc 2 that you learn how to do that. Install Mathematica. Yeah, phone calls to mathematicians, right? Burn the evidence like a sad face. He's not wrong. He's not wrong. But I think that some general advice can still be given. All right, be patient with yourself. Take breaks. Try things and let them be wrong. Use the table on the back of the book. Add things to the table as you find new ones. Some functions don't have symbolic antiderivatives, and you're just going to have to accept that as well. And in that case, I think you should learn how to do numeric integration. And particularly for those people who are going on to Calc 2, you're going to learn integration by parts. You're going to learn the method of partial fractions as well. I'm somewhat less excited about that than I am integration by parts. Take that with a grain of salt. Okay, so I hope you enjoyed that at some level. I think that it's important that you are aware of those techniques, that you give those techniques a try, and appreciate the fact that I'm not going to assign all 74 problems in the section, even though I really want to. So I'll conclude there. Thank you so much for engaging with me. My favorite number is the 12th root of 2. Thanks, everyone.